Yeah. So we have reached 40. So should we start, guys? What do you think? Anand Prasad, Ananya Rawat.
Yes, sir.
Should we begin?
Yes, sir.
Okay. Okay. Can you see the presentation, guys?
Yes, sir.
Fantastic. तो शुरू करें लेके प्रभु का नाम चलो so we have been talking about beams, steel beams, and for example here there is a case study of a failure of a beam. That is so there's a section given and the failed photograph given. Now, the data is that prior to and during placement of the concrete deck, the top cross section was closed only by stay in place forms, which are not provided, which do not provide sufficient torsional strength or stiffness. Now, this is very interesting because once you end up getting your concrete beam in place, the section becomes fairly stable because the concrete and the steel together ends up acting like a closed box. But until concrete was placed, it was just this tub which was there, and with these brackets kind of a thing. And this system was not able to generate. So basically the shuttering was being done just from the section itself. So you ended up having a kind of a stay which was holding this plywood in place, and that was being used as your system to cast this concrete deck. So when this system itself was not providing a sufficient torsional resistance, so when you cast the concrete, this system failed, and then the entire system ended up collapsing. Now, the strength of this system was sufficient that it would not have failed because of pure flexure. But the torsional stiffness of the section was fundamentally something which incorporated the concrete deck as a part of this entire system. In the absence of the concrete deck, when you just cast wet concrete, the section was not giving a significant torsional resistance. And you ended up getting a kind of a failure kind of a system happening. Because instead of becoming a closed box section, it was now only a open box section which was existing. So this ended up giving, so the concept of this kind of a system is also telling you that it is not just the final design which needs to be evaluated, it is also the design uh, during construction. So the loads which are coming during construction also need to be evaluated to see that the system is going to be stay safe. So I think this is a very interesting kind of idea which comes in, that it is the final sections of very many structures are safe, but during construction there are certain stresses which develop, which the system is unsafe for, and collapse can happen for those kinds of things also. So it's not just the final loads and stresses which need to be checked, but also the intermediate kind of systems which generate failure. Uh, Now the concept is that, like in your like when we talked about lace columns, we had a column, and you ended up getting some kind of a lacing system, so which reduced the effect. I mean, which kind of made the system act as a composite whole, And it also ended up giving you a L effective by R, where R was now the cross section, the generalized cross section. And at a local level, you ended up getting a much smaller L, which needed to be addressed. Similarly, when you're doing bracing on beam, that is the kind of a thing that you're doing, that you have got a compression flange, and then you want to kind of apply some kind of a braces so that the effective length of the compression span becomes less than the actual L of the beam. Because the failure of the compression flange ends up as becoming based upon whatever is the L by R of the section. And this L depends upon what is the unbraced length. Now, again, what is very interesting is it is not just giving some kind of bracing which will ensure that your L is reduced, because now the entire system can deflect as a single rigid body. So you can end up getting a shape which is like this, with your bracing just having a rigid body movement kind of a system happening. Now, if this is possible, this does not act as an adequate um, bracing, and is actually an inadequate bracing. Whereas in the other section, you see that this bracing is connected to a wall. It's anchored into a wall here. So when it is anchored into a wall, these points end up becoming kind of fixed points. And instead of that section, which is that as being the deflected shape, you end up getting that as a deflected shape, because these points end up getting fixed in place. Now, once you end up getting these points which are fixed in place, you end up getting a system which ends up acting as a bracing system, because you have just a rigid body movement of the entire system. Is this making sense, guys? Somebody, man.
So
Yeah.
once again,
Okay. So you have two beams, which is, this is one beam and this is one beam, and you have got these as your braces. Now, when this beam deflects in this way and this beam deflects in this way, this bracing can just translate as a rigid body motion. Now, if a bracing can just translate as a rigid body motion, it cannot actually provide effective bracing, because bracing means that you want to fix these points so that they don't relatively move. Because when you fix these points, as you get when you get a bracing which is anchored into a wall, you cannot get this behavior any longer, and it is replaced by that behavior. Is this making sense?
yes, sir.
So, which is why in this we can say that this is an adequate bracing and this is not an adequate bracing.
Got it, sir.
Okay. Similarly, you can have intermediate braces. Now, the thing is that once you triangulate a system, this prevents this kind of a movement from happening, because when you look at a rectangle, and a rectangle kind of goes into a parabola, or goes into a trapezium, this is an increased dimension, this is a reduced dimension. Now, if you have a triangular bracing in place, you can ensure that this system cannot deform into that. Is this making sense?
Yes, sir.
So a triangular diagonal bracing is becoming an effective bracing for a beam system, because it prevents a rigid body translation, as what we had seen in the earlier system. So this can always translate as that without any change in length, but this cannot translate into that, because for this to translate into that, this length has to increase, this length has to decrease. So basically, there is a certain resistance against this changing in dimension, which ensures that diagonal bracing ends up as becoming an effective bracing. Is this making sense?
Yes, sir.
Now, what is very interesting is that it doesn't need to be a diagonal bracing for every bay. So if you have got several bays, If in only one day I give a diagonal dressing, what happens is that rigid body movement is not possible in this. Are we good with this? Is this making sense? That if I give diagonal bracing in one bay, these two bays cannot have a rigid body displacement. Is this making sense?
Yes, sir.
Now, because this bay cannot have a rigid body with respect to this, you cannot have a rigid body in the entire system, because for this rigid body to happen, this also has to be a rigid body movement. Is this making sense again?
Yes, sir.
So putting diagonal bracing in only one bay of an entire system also ensures that the rest of the system, even if it is just a horizontal bracing, is still effective. Is this okay?
Yes, sir.
So these are different types of cross
Please start
bracing.
the recording.
So it has not started, is it? But are you not listening to this?
Yes, sir, but later on we can also listen.
Okay. So basically, I'll have to get out of this and do something. Just a minute. There you go. Happy?
Yes, sir.
अब क्या पेन हो गया यार? Anyway, देख. Hide, share content, then share screen one. Fantastic. Can you see the screen now?
No, sir.
What about now?
No, sir.
कुछ तो प्रॉब्लम हो रहा है यार.
So you started sharing for a minute, then yeah, now it's visible, sir. Your Teams window is open.
Okay, fantastic. Now,
Now, sir, right now your Teams window is being shared,
Okay.
not the slide.
what about now? Okay, my Teams window is being shared. Okay, so I need to
So
stop
first open
sharing.
the other slide.
It is open, beta. I mean, you have to open the PowerPoint. No, that's what you're saying.
Yes, sir.
The PowerPoint is open. And then I go to my this and share options. And I have to go to screen 1 because that is actually what where the PowerPoint is. Where's your shared window? Sharing
No,
is
sir.
paused until you return to the shared window. So where is the shared window? Oh, I know what is the problem. Okay, let me stop recording for a minute and share now, which you should now get it. कुछ तो बकवास हो रहा है यार.
So you can share your screen instead of sharing a window.
Yeah, but when I'm saying share contents, it talks about sharing a screen only, na? It talks about sharing screen 1.
So share your desktop window, desktop
वो
instead
तो,
of. So you
there
have
is
opened.
no whiteboard. You have no clue what is happening. No clue, man. Completely no clue. Screen 1, I'm going. It is not showing anything. It is allowing me to share everything else. Hey, you know what, guys? I'm just going to log off and log on again. Okay. Hello.
Yes, sir. Your screen is visible.
Is the case
We can
is
see the
the
slides. Case study
can see
failure
this?
of Marshall Bridge.
Fantastic, brilliant. Okay, so but now we have to start recording also, ना? क्या बकवास है यार, इसमें यार क्या पेन है पता है ना आप लोगों को. अब start recording. तो चलो record होना शुरू हुआ. But can you still see the PowerPoint? Is the PowerPoint still visible?
Yes, sir.
Fantastic. So now it is recording and the PowerPoint is visible. So brilliant. We have solved a huge technical problem. I'm feeling so happy with myself. Okay. So this is the cross beams and bracing which is happening. You can see these are your, what the hell is going on here? क्या बकवास होता है यार life में. Okay. You can see these are your main beams, and you can see these are your bracings. Is this making sense?
Yes, sir.
Okay. So these are the cross beams bracing main beams. Bracing requirement. There's a relative stiffness, which is given by this, which is your empirical formula. And it is this which is given for your nodal. And this is your strength, which is needed for your bracings and for your nodal, for your discrete, relative and discrete bracing systems. Okay. So one is the stiffness and one is the strength. So if you see this, if you see the relative bracing, which is where you're bracing one system relative to another, the requirement for strength is much lesser, is when you're actually bracing a system as a nodal discrete system kind of a thing. So you also, if you look at the stiffness of this is much higher than the stiffness of this. So the relative system is a system which is bracing one member relative to another. And a discrete nodal system is a system which is doing a generic bracing system. So, so when you ended up getting a system which was doing just that, what you're having is a relative bracing, which is just bracing this beam relative to that beam. When you end up getting a nodal system, you are getting that kind of a system in place, which is doing a generic bracing of the entire system. So the strength requirements are this, and the relative stiffnesses are this. We'll take an example where at some point of time where we can talk about this at a greater length. Torsional bracings. Now, the torsional bracings are the diaphragms end up as becoming torsional bracing. So basically, if you end up getting some kind of a diaphragm system which is holding your beams together, that ends up as generating your torsional brace, which is something like this. So you can get a kind of a, if you have a strong diaphragm, you can end up getting a web distortion, which is possible in a torsional bracing system. You can have through girders, which end up also becoming a torsional bracing system. And so basically the thing is that you are ending up getting this one beam and this one beam. You are ending up getting these beams rotating with respect to each other. And this ends up becoming the system which prevents that rotation from happening. Or you can end up getting the same kind of a thing, and you can end up getting a diaphragm which prevents that system from happening. So these are the two different kinds of fundamental bracing systems that you can look at. That one is either, so basically a system of torsional bracing ends up having a strong bracing system which prevents this lateral twist, which is otherwise possible to be generated. Is this making sense?
Yes, sir.
So the case study of Tacoma Narrows Bridge, I think this is one of the most studied structures in one of the most. I don't think I have a video of this, but sometimes go to Google and do a Tacoma Narrows failure, and you'll see the entire bridge before failure of just flipping around and turning around, and yeah, it's a fairly cool looking thing. This bridge was made, I think, sometime in the 1930s. It was called the Galloping Gertie because even from the time that it was made to the time that it collapsed, it was a bridge which always was moving around a lot. So it was not possible. I mean, it was always an experience for somebody driving on this bridge. And under some kind of a wind flutter condition, you ended up as getting a kind of a torsional vibration mode, which was caused by fluttering. And you ended up getting a failure because of that. So take a look at the video at some point of time. I'm not showing it to you here, but take a look at it sometime to see how this actually behaved. Now, after this background of what is the entire concept of beam behavior and what are the different kinds of bracing systems and what is that flexural and torsional and everything, now we get into actually figuring out how the actual system works. So if I take a look at a material, if it is within the elastic limit, you end up getting this as your strain diagram and equivalent stress diagram, which is proportional to your strain diagram. This is the diagram that you get of stress and strain until you reach the yield point. At yield point, you get a yield point value there, a yield point value there, and you still get a straight line strain diagram and equivalently a straight line stress diagram. Now, once you give a rotation which is more than what is that which generates the yield strain, you get a post yield behavior where your strain still remains so you fundamentally end up getting a system where plane sections remain plane. So your strain is always going to be a straight line diagram, but stress now starts ending up as becoming a trapezium, where this point, which is corresponding to this point, and this is the yield strain value, this much. That is the yield strain, and that corresponds to your yield stress. And beyond the yield stress, you get a rectangular feature. As you increase it more and more, this trapezium keeps increasing in size until eventually, at some point, you will end up getting a rectangular stress block where you're saying that the entire cross section is in yield. Is this making sense?
Yes, sir. But we would not
So,
reach that point.
I'm sorry. Have you done this in your solid mechanics at some point of time?
Yes, sir. So
Okay.
we talked about it in the class too.
Okay. So I think, therefore, that this entire concept ends up as being correct. From this, which is your partial plasticity, you eventually reach what is a total plastic behavior. And this moment at which total plasticity is reached, after this moment, you end up having this section can take no more moment and it behaves as a plastic hinge. That giving a greater rotation will make this section rotate without having any increase in its moment taking capacity. So your moment ends up as following. First, there is some kind of a moment. It reaches your elastic moment, which is where yield is first reached. And from yield, it finally reaches your plastic moment, beyond which it forms a hinge. So if you look at a graph, it would be something that there's an elastic moment, there's a plastic moment, and then there's a hinge. So this is the kind of behavior that a section is fundamentally looking at behaving. Now, this is usually made by joining this and made into a elastic plastic kind of a sectional behavior, whereas the actual behavior is always going to be an asymptotic behavior, but this is your generalization of that behavior. And this, the dark spots that you're seeing is what is the onset of plasticity in the system. That from no plasticity, there is a certain amount of plasticity to a higher amount of plasticity. And when this triangle on top meets this triangle at bottom, which is here, you have got a total plastic section. Is this making sense, guys?
Yes, sir.
And eventually the beam keeps deflecting further and further till a place where it actually eventually becomes a plastic hinge. Now, coming to design of laterally supported beams. And it's very interesting that after doing all this work, okay, you get some extremely simple formulae for designing of beams, which makes me always believe, yaar itna kaam humne kiya kyun? But chalo theek hai, kiya hai. Where MD is nothing but beta B, which is some constant, times Z plastic times Fy by lambda m naught. Okay. Z plastic is your plastic section modulus, which is fundamentally just saying sigma is equal to m by z, or m is equal to z times sigma. Now, this z times sigma becomes zp, which is your plastic behavior, times sigma, which is fy by lambda m naught. And you're just adding a beta b in this, where beta b is very simple. Beta b is equal to 1 for plastic and compact sections, and beta b is equal to ZE by ZP for semi-compact sections. So the formula is basically saying that जब plastic or compact sections होता है, तब M is equal to ZP into sigma, और जब semi-compact section होता है, the M is equal to ZE into sigma, and which is fundamentally our definition of semi-compact and compact section, where semi-compact section was that Fy is possible, but bending beyond Fy is not. Compact was Fy is possible, plastic is possible, but rotation around the plastic hinge is not. And plastic section was not only is a full plasticity possible, but rotation is also possible around plastic hinge. Remember, this is what we had defined when we talked about plastic sections, compact sections, and semi-compact sections, where we said semi-compact में Fy पहुंचता है, compact में plastic पहुंचता है, और plastic में plastic पहुंचता है, plus rotation होता है. So plastic plus rotation is a plastic section. Just hitting plastic is a compact section, and reaching elastic yield is a semi-compact section. A section which cannot reach elastic yield was called a slender section. Remember, we had talked about this in class when we had talked about the different types of sections. Of course, we had talked about it in the context of compressionless, but the system remains the same no matter whether we are looking at this or that. Is this cool?
Yes, sir.
So this ends up as becoming the entire system. And we say that beta B ZP has to be less than or equal to 1.2 Z elastic for most sections, and is less than or equal to 1.5 Z elastic for cantilevers. So if a section is so the basic concept is that it is always going to be beta B ZP times Fy by lambda m naught. Now the thing is that beta B ZP is limited to being 1.2 ZD. So you cannot have a ZP greater than 20% of Z for a regular section, and you cannot have a ZP greater than 1.5 times ZD for cantilever sections. Is this making sense?
Yes, sir.
Fantastic. And your V is nothing but AV times FYW by root 3 lambda m naught. And again, here if you remember your Bolt theory, your shear strength was always Fy by root 3. So this is just AV times Fy by root 3 and lambda m naught. where when you're looking at shear, you replace Fy by root 3, because if Fy is your tensile strength, Fy by root 3 ends up as becoming your shear strength. And this is, of course, assuming a Tresca failure surface. I'm not going to get into different kinds of failure surfaces because you've got von Mises, you have Tresca, you have Coulomb, you have Drucker, you've got all these which are different types of failure surfaces. We just say that this is what your failure surface is, that if it is an octagon in some kind of a sense. So your fundamental concept is that your Moore-Coulomb failure surface is an octagon. The Drucker-Prager is an ellipse, which is kind of inscribed in this octagon. Your von Mises, which is the concept that what is your maximum so the Tresca is maximum shear stress, which is your failure surface, and von Mises is the maximum first stress invariant, which is the failure surface. So these are the different ways that failure surfaces are defined. I'm not going to get more into this because for that we need to. It's actually a solid mechanics part, so I don't want to take it up into design. But this is just idea that there are different failure surfaces, and it is Tresca which is fundamentally used in steel, which ends up giving you a Fy by root 3 as your shear strength for a Fy tensile strength. Is this cool? So we are just replacing your tensile strength by Fy by root 3, and other that gives you your shear failure. Is this making sense, guys? Is this okay? Is this making sense? Somebody, guys, is this all right? Someone? Would someone like to help me out here?
Yes, sir.
Fantastic. So, we go to the next slide. And this is the design of a laterally unsupported beam, where the laterally unsupported beam just adds a very interesting reduction value, where instead of Fy by lambda m naught, it is nothing but x LT times Fy by lambda m naught. So the concept between the difference between a laterally supported and a laterally unsupported beam is this reduction factor. So if a beam is laterally supported, you just do Fy by lambda m naught. And if a beam is not laterally supported, we do some reduction factor times Fy by lambda m naught. And XLT is nothing but 1 by phi plus phi squared minus lambda squared raised to 0.5, where phi is equal to 0.5 times 1 plus alpha times lambda 0.2 plus lambda squared, where alpha is 0.21 for a rolled section and alpha is 0.49 for a welded section. So basically the concept is that are we using a rolled section or a welded section? So if you're using a rolled section, you use alpha as 0.21. If you're using a welded section, you take 0.49. These are the only two values which are there for alpha. Plug that alpha into this equation. No, but to plug it into this equation, you need to find out what lambda is. And what is lambda? Lambda is nothing but our good old friend Fy by F critical, which is the same thing that we had used when we had looked at your column theory. So, and what is F critical? So F critical ends up as becoming 1.1 pi squared E by L squared, and some kind of empirical formula which gives you M critical. What is Fy? Fy is known to you. So you know Fy, you know L, you know R. Find out what L by Ry is. So when you know L by Ry, plug L by Ry here and you'll get what is F critical. Fy by F critical, and then square root of that will give you lambda. Take this lambda, go to this equation, plug it in here. With alpha, you'll get what is phi. Take phi, plug it in there, and you'll get what is XLT. Phenomenal. So if you don't want to do all of this, go to the code, take a look at a thing. You're getting a thing which is L by R and different Fy, and what is different values of F critical. That's cool, right? So you don't need to do all this calculation. You can just go to that code, see a table there which gives you these values, and there, you've got it. Are we good with this? You want to take a look at that code value? Let's go and open. Where the hell is it? Yeah, should be there somewhere here. Standards. Yeah, IS 800. Can you see my screen, guys? Guys, and you can see my screen?
Yes, sir.
Fantastic. There we are. So yeah, this is F critical B. This is KL by R. This is H by TF. Based upon what is KL by R and H by TF, you can just go down here. So fundamentally, if I know L by R and I know what is H by TF, H by TF is the total section divided by the thickness of the flange. The total height divided by the thickness of the flange is at TF. I know what H by TF is. I know what KL by R is. I can just go in here and find out what F critical B is. I know what F critical B is. I go here and this is F critical B. These are different values of Fy, and find out straight away what my FBD is. Is this making sense? And FBD ends up giving me this directly. So it is beta B ZP times FBD. FBD, I take a look at it from this part of the code, which is knowing what are different Fys and different F critical B. I can find out straight away what FBD is. And F critical B, I work out by looking at what is KL by R and H by TF and find out what F critical is. So do you see my point? You first go to table 14, figure out what is your KL by R, figure out what is your H by TF, go down here and find out what is F critical B. Take this value of F critical B, come here and say, this is F critical B, this is Fy, this value here is FBD. Take this FBD, multiply that by beta B and ZP, what is your bending moment, your design bending moment as far as your code is concerned. Is this making sense, guys?
Yes, sir.
Phenomenal. So after talking all about different kinds of torsion and different kinds of bracings and different kinds of everything, yeah, what your steel design effectively ends up as is just these two slides and these two equations. The rest of it is just for you to understand where this shit has come from. But end of the day, that's just about it. Is this making sense, guys?
Yes, sir.
And then when you take a look at shear strength of steel beams, okay, you take a look at shear yielding. So this is the way that the shear yielding happens close to the surface, that the surface doesn't go down, this place does. This is the domain of maximum shear. So you end up getting a maximum shear deformation which happens in this area. And this is telling you what are the different values of shear areas that you have to take. So the shear area is not the gross cross-sectional area. The shear area is whatever is the web. So the flanges in a beam are fundamentally those which take flexure, and the web of a beam is fundamentally that which takes shear. So if you take a look at all of this, fundamentally your shear area is nothing more than the total length h multiplied by what is the thickness of the web. The total length h multiplied by what is the thickness of the web. This is of course for a hot rolled section. And for built-up section, it is not the total length, it is the length between the two flanges, because these two places are welded together, so you do not assume that it acts like a continuous system. So for that, it is just D times TW. Or in this case, 2H, 2B times TW. So depending upon how your section is. So it is this D, which is the distance between the two welded faces, times TW. That ends up as becoming your shear area. So if you know your shear area, you know that AV times FIW by 3 root 3, that is your shear, that is your design shear strength of a section. Is this okay? Talk about web buckling and web crippling in the next class. But until now, we have been able to figure out how to design a beam which is laterally supported, how to design a beam which is laterally unsupported, and to design a beam for shear. Are we good with this till now?
Yes, sir.
Fantastic. So I think I'm going to stop here and ask if you have any questions, and if you have any questions, address them. Otherwise, yeah, thank you very much, and I'll see you next time. Yeah, so thank you very much, and I'll see you next time. Have a great Tuesday. I'll see you on Wednesday.